Welcome to Global Future School students. This is your first year chemistry class. I am Dr. Zalwano. The topic for today's discussion is molecular orbital theory from chapter 3, that is the theories of covalent bonding. Students, basically molecular orbital theory, this chapter is the continuity of the previous lecture. In previous lecture that was also about molecular orbital theory, we discussed its postulates and some applications for smaller diatomic molecules. But after completing now, including this topic, students, you will be able to understand the diamagnetic and paramagnetic behavior of some of the molecules. I already told you that paramagnetic behavior is that some molecules shows response towards the magnetic field, like oxygen, and that is due to presence of partially filled molecular orbitals, not the atomic orbitals, in antibonding or bonding. If they have some partially filled molecular orbitals, then they show paramagnetic behavior, but if their molecular orbitals are completely filled, then those molecules are diamagnetic. They have diamagnetic behavior, and you will also be able to calculate the bond order of the molecules. Bond order basically shows the number of bonds between two atoms. And now we have the applications of molecular orbital theory for homonuclear diatomic molecule. First I will clear you. Diatomic means a molecule that is formed by two atoms, and homonuclear means a molecule that have two atoms and those two atoms are from same element. This is like H2, like N2, O2, F2, Cl2, and so on. So these are basically molecular orbital theory for homonuclear diatomic molecules. First of all, we discuss the molecular orbital theory. According to molecular orbital theory, the N2 molecules, and you know, first of all, you have to write the electronic configuration of nitrogen. You know, atomic number of nitrogen is 7, and its electronic configuration is like 1s2, 2s2, 2px1, 2py1, 2pz1. So they have total 7 electrons. And the second nitrogen will also have the same configuration, like 1s2, 2s2, 2px1, and 2py1, and 2pz1. So this is the second shell, and this one is the first shell. So now I'm not drawing for 1s2, 1s2. This is the same as like helium, and for 2s2 I will draw because this is in the second shell. For that, as I already told you, that this is the energy increase from lower to upward. This is energy axis, and this 2s from first nitrogen, it is like 2s, and this is of the same energy level, and the second 2s. And according to molecular orbital theory postulates that those atomic orbitals that are of same energy and same shape, they overlap to form the molecular orbitals. And how many molecular orbitals? That will be equal to the atomic orbital overlap, and out of them half of 2 is 1 is of lower energy than parent atomic, and half will be at higher energy than their parent atomic orbitals. And you know, in 2s there are 2 electrons, and in other 2s there are also 2 electrons. Now fill the electron according to Aufbau, Pauli, and Hund's rule. You have total 4 electrons, so electron will go first to the lower molecular orbital, 1, 2, and then to the higher antibody molecular orbitals. So S and S, they form sigma. So this is 2s sigma bonding molecular orbital, and this is 2s sigma star. Sigma star, or you can say sigma star antibody molecular orbital. You can also write sigma star 2s or sigma star 2s, this one. So and now we come towards these. Now nitrogen is like This is at higher energy than these two s. So you have 2px, 2py and 2pz. So all of the atomic orbitals will be drawn like a spherical shape. There is no need to write the dumbbell shape. Just because they are at the same energy level, they are degenerate orbitals. You can give any name to 2p. This is 2px, 2py and 2pz. So this is also a 2px, 2py and 2pz. Now come to the electrons. How many electrons in the atomic orbital? 1, 2, 3. All contains 1. They are partially filled. Second, they also will have same. And now there are 6 atomic orbitals. They will overlap to form 6 molecular orbitals. Out of them, 3 will be at lower energy and 3 will be at the higher energy. So first 2px, they combine to form sigma 2px, and the remaining py and pz, they will form, because they are of the same energy, they will form pi 2py and pi 2pz, and half of them will be at the higher energy. Then parents, that is sigma star 2px and pi star 2py and pi star 2pz. Now fill the electron according to the Pauli exclusion Hund's rule. You have total 6 electrons. Start from the lower energy levels 1 and now 2, because they are of the same energy level. So first one will go, then the next one, 2, 3 and 4. Now you have 2 more, 5 and 6. So electrons are completely filled in molecular orbitals, that are bonding molecular orbitals. Now you have to write the bond order. So bond order is number of electrons in the, because you can find the bond order by adding these two diagrams, or you can find from here. There is no need to write this, because number of electrons in bonding and number of electrons in anti-bonding are same. So you can find out with the help of only this diagram. 6 minus number of electrons in the anti-bonding, there is no electron in the anti-bonding, so 6 minus 0 divided by 2, so you got the answer 3. Answer 3 means nitrogen has triple bond in between them. Bond order 3 means nitrogen and 2 nitrogen, they have 3 bonds between them. Now write the energy order. Energy order. So start from here, from lower to higher, then come towards this, from lower to higher. So first of all, sigma, so this is sigma 2s less than sigma star 2s less than, now these pi 2py. Now you can see pi 2py and pi 2pz are of the same energy. So equal sign, pi 2pz less than sigma 2px less than pi star 2py equals to pi star, because again these are at the same energy level, pi star 2pz, that is less than sigma star 2px. So this is the energy order for the nitrogen molecule. Here you should notice that sigma 2px is at little higher energy as compared to pi 2py. Basically, I will explain in detail the reason. I will just let you know the difference of energy between 2s and 2px is 2p is very low, and then just consider that before overlapping they intermix to form the p orbitals. They obtain like s character, while the s orbitals they attain like p character. So both are sp like. Then they overlap to form the molecular orbital, and due to s they got p character, they are at little higher energy, and the px they got the px got the s, and py pz they also got the s character. Due to attaining s character they are at lower energy, while px they are raised to at little higher energy level, sigma molecular orbitals. So that's why energy, there is energy difference between atoms of having time number 7 or less, and the atoms that have atomic number 8 or more, they have a little bit different energy order. I will explain you in next slides. And now come to the either this is paramagnetic or diamagnetic. Students, you know paramagnetic mean if they have any partially filled molecular orbital, and here you can see this molecular orbital is completely filled, this molecular orbital is completely filled, this is also completely filled. So nitrogen, it is diamagnetic. If you want to draw for N2 2 positive, 2 positive mean removal of electrons. 2 positive mean removal of 2 electrons. I'm just drawing for you 1 1, because this is now N positive and this is now N positive, so both of they have N positive 2. Remaining energy diagram will be same. Now I am not writing the names, you can write and you should write. Now fill the electrons 1 2 4, 1 2 3 4. What will be the bond order? 1 2 3 4, 4 minus 0 divided by 2, so answer is 2. So nitrogen and nitrogen, when they have 2 positive, they have 2 bonds between them. And energy order will be same, like exact this one, sigma 2s sigma star, and this pi to py, pi to pz, sigma to px, these are pi star to py, pi star to pz, and this is the sigma star to px. And again this is diamagnetic. Why? Because it has a molecular orbital that are completely filled. Now come to the point now for N2 2 negative. Since for 2 negative, N2 2 negative means getting 2 electrons. So already nitrogen has 1 2 3, and if it got one more electron, and other nitrogen also got one more electron, now what will be the electronic its behavior? I'm writing in this again. First, this is like nitrogen and regular nitrogen, 1 2 3 1 2 3. Now if it is negative, negative mean gaining of one electron. Now negative mean gaining of one more electron in both. So now fill the electron. Now 1 2 3 4, and you have total 1 2 3 4 8, 1 2 3 4 5 6 7 and 8. So here Hund's rule is applied. Electron will go into separate orbital because these are degenerate orbitals. Rather they live in one, and one is empty. So now in case of N2 2 negative, it has a partially filled atomic orbit, molecular orbitals. N2 2 negative is like paramagnetic. While N2 2 positive and N2 neutral, they are diamagnetic. Students, hopefully this will be clear for you. But they have the energy order same like this one. Just filling of the electron is different. And now remember this, I will discuss this in the next lecture in next slide with reference to the oxygen. In this case 2px are raised to at higher energy, while 2py and 2pz pi, these pi are raised to lower, they were moved towards the lower energy. So for oxygen, its atomic number is 8, 1s2, 2s2, 2px2, 2py1, 2pz1. And the second oxygen, this is also same, 1s2, 2s2, 2px, 2py1 and 2pz1. So this is the first shell and this is the second. Out of them I am drawing for this one and then for this one. This one is like energy in the from lower to upward. Oxygen, that is 2s, it has 2 electrons. Other oxygen like 2s, 2 electron, they will form molecular orbitals. Half of them will be at low energy, half of them will be at high energy. So this is sigma 2s and this is sigma star 2s. 4 electron, 1, 2, 3, 4. So electron bonding and anti-bonding, they are same. Now for oxygen like this one is like 2px, 2py and 2pz, and this is like 2px, 2py and 2pz. 2px, 2py and 2pz. 2px, 2py and 2pz. And they contain 1, 2, 3, 4 and 4 electrons in this case. Out of 6 molecular orbitals will form. Out of them half, means 3 will be at lower energy level. This is sigma 2px and this is pi 2py and pi 2pz. And half of them will be at high energy, sigma star 2px and pi star 2pz and pi star 2py. Now fill the electrons. You have total 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4, 5, 6, 7, 8. So it will be diamagnetic. It will be paramagnetic. Why? Why it is paramagnetic? Because oxygen, there are partially filled and half filled molecular orbitals. That's why oxygen shows behavior towards the magnetic field. And its energy order you can write easily. Look at here, start from here to up and then from here to upward. First write the lower energy, sigma 2s less than sigma star 2s less than sigma 2px less than pi 2py, that is equal to pi 2p z less than pi star 2py equals to pi star 2pc, and it is less than sigma star 2px. So this is the energy order. So difference with nitrogen is here. In that case, sigma 2px was raised to a higher energy, while pi orbitals, molecular orbitals were towards the lower energy. And this is actually because in this case the difference of energy between 2s and 2p are greater, and they do not intermix to attain s or p character. And now come to if it is 2 negative. 2 negative means 1 electron more, gaining of 1 more electron. If it gain 1 more electron, so I am just drawing this for you. Rest of the energy diagram will be same. Just I am explaining you the distribution of electrons. This is a normal configuration, like of oxygen, but O2 1 negative means there is 1 more electron. You can write in any oxygen. Now filling the electrons, you have total 9 electrons. 1, 2, 3, 4, 5, 6, 7, 8 and 9. So it has still partially filled. Its paramagnetic behavior will be of low magnitude, but still it is paramagnetic. So this is for O2 single negative. Now if it is 2 negative, then one electron will be more here and this will come here. So now O2 negative, this will be diamagnetic. Why? Because there is no partially filled molecular orbitals. And you can also obtain the calculate the bond order. In this case 1 2 3 4 5 6 minus 1 2 3 4 divided by 2, 6 minus 4 2, 2 by 2, so 1. So if it is O2 negative, then there will be single bond if it is 2 negative. For 1 negative, bond order will be different. For O2 positive, bond order will be different. For O1 positive, bond order again will be different. So now come to this point, why it is different for nitrogen, boron, carbon, you can say atoms with atomic number 7 or less, and atoms with atomic number 8 or more. So diatomic molecules or their ions. So the behavior of energy order for atom and their ions, either positive or negative, will be the same. For example, in this case, for oxygen, I just explained you in previous slide that sigma 2px at lower energy and pi 2py, pi 2pz at high energy. But in case of nitrogen, boron, carbon and their ions, here in this case, this sigma 2px is at higher energy as compared to pi 2py and pi 2pz. So why there is a difference? This is there is a reason why they have various energy order. This you can see. Actually, there is a difference start from here to at this point. That shows 2px at higher energy as compared to this one. This is actually due to mixing of, I already told you that 2s and 2p atomic orbitals, and because energy, and the other reason is energy difference. Energy difference reason, what is the energy difference reason? There is the low energy difference actually in them. That's why there is possibility of mixing of these orbitals like hybridization. So before forming or overlapping to form molecular orbitals, they hybrid to form atomic orbitals or hybrid orbitals, then they form the molecular orbital. As a result, sigma 2s and sigma star 2s molecular orbitals, they do not retain s character, while the p orbitals, they do not retain their p character. Actually, all of the molecular orbitals, they acquire sp character, and due to this mixing, sigma 2px and sigma 2p star 2px becomes less stable and they are raised in energy. But as pi 2py and pi 2pz are of the same energy, they remain unchanged. But sigma 2px is raised to such an extent that it becomes higher in energy than pi 2py and pi 2pz, as I have discussed in the molecular orbital diagram as well as in the previous slide. But oxygen and fluorine, there is no intermixing, and they do not do so because the reason is high energy difference of their 2s and 2p. In case of oxygen, the energy difference between s and p, 2s and 2p, is 1595 kilojoule per mole, and for fluorine this energy difference is even more, that is 2078 kilojoule per mole. But in case of nitrogen, boron and carbon, for boron the energy difference is very low, that is 554 kilojoule per mole, the difference between 2s and 2p. And for carbon the energy difference is only 846, and for nitrogen the energy difference is even 1195, that is less than the energy difference of for oxygen and fluorine. That's why 2s and 2p, they intermix and they attain the s and p character. So they sigma 2px, they attain p character, and they are unstable and raised to higher as compared to pi 2py and pi 2pz. and these energy differences have been calculated by spectroscopic techniques. Properly these have been calculated. Now come to the what is the difference of valence bond theory and molecular orbital. There are a lot of points which explain the molecular orbital theory, which do not explain the valence bond theory, and vice versa. First, according to valence bond theory, the only valence electrons are involved in bond formation, but according to molecular orbital theory, all the electrons of interacting atoms that is part of molecules, all of its electrons are involved in bond formation. Next, according to molecular orbital theory, the two concerned atomic orbitals do not lose their individual identity, but in molecular orbitals we've already learned that they lose their identity. They after overlapping they have different energy, so they basically lose their individual identity. And according to valence bond theory, valence bond theory doesn't explain the paramagnetic behavior of the oxygen molecules and some other molecules that show the paramagnetic behavior, but only the molecular orbital theory, it shows the paramagnetic behavior, that is also called electrical properties of the some of the molecules. Valence bond theory do not give idea about the bond order, how many bonds will be formed between two atoms, but this idea was given by molecular orbital theory if the bonds between two atoms is single or double or triple bond. And according to valence bond theory, in that do not explain the non-existence of helium molecule. According to valence bond theory, there may be helium molecule, but molecular orbital theory with proper bond order calculation, it shows that helium do not exist as He2 molecule. Now students, after this practice, lot of questions I solved for you, I draw the molecular orbital diagram for you. Now this is your turn to practice the question and draw the molecular energy level orbital diagrams of some of the molecules and their ions, and you have to write their molecular orbital diagram, their energy orders, and also have to calculate the bond orders. And in that you will have to tell either a molecule has paramagnetic behavior or diamagnetic behavior. I have drawn for oxygen as a neutral molecule. So 1 negative means add 1 electron in, 2 negative means 2 negative. I have already drawn for this O2 and O2. 1 positive means remove 1 electron, 2 positive means remove 2 electron. Fluorine and oxygen, they have the same type of molecular orbital diagram. Just take care how many electrons are in fluorine, and I have already drawn for N2, that is neutral, and also I have explained with reference to negative 2 and positive. So draw the molecular orbital diagrams for all these. If you successfully draw the molecular orbital diagrams for these molecules, then it means you have a full understanding, and you can attempt any type of the question asked from the molecular orbital theory. So this was all about the molecular orbital theory and its application, and our next topic will be bond energy.